Hi, welcome to this August edition of 30 Minutes with Link Spring. We're happy to have you all with us. Today's subject is on variable frequency drives. Variable frequency drives play a critical role in the efficiency and performance of a building. They help increase system reliability, maximize equipment lifetime value, contribute to saving energy, lower maintenance costs, and add to overall smoother operations. Presenting with us today is Margaret Shaw, HVAC Strategic Accounts OEM Manager with Franklin Control Systems and also a Link Spring Drive partner. Margaret will provide some drive basics, look at what is a drive and what is it doing, and cover the difference between starters and VFDs. She also will provide some insight on when to use one or the other based on your application. Finally, she will also review the different drive packages and what each entails, and how to make sure your bases are covered when selecting your product. We will be recording the session, and it will be available in a few days. When it comes to questions, if you do have any, please be sure to use the question function. All right, let's get started with Margaret.
Hey, good morning, everyone. Thank you all for being here. This is my first time doing a webinar where I'm not interacting directly with people, so this will be kind of a new thing for me. I can't believe I actually have a soapbox. Nobody can interrupt me. Who knows what I could do? So yeah, Tanya, if you just want to go ahead and move to the agenda slide. There you go. So yeah, just like Tanya was saying, we're going to kind of take a bird's eye view of basically what you're working with when we're working with drives, right? So we're going to talk about just the basics. So like, what is the drive doing? What is actually happening inside of this drive that's speeding up and slowing down your motor? Why do you guys care about using drives? Why are they important for you and for your customers? What are some various packages that you guys can expect to see? And then, of course, we'll open up the floor for question and answer. Go ahead. Go ahead. All right, so first things first, let's talk about some of the different forms of motor controls that we're going to see. So the first and most basic thing we're going to see is a magnetic starter, okay? This is referred to as an across-the-line starter. This is full voltage, non-reversing, 100% on, 100% off. Your starter is a light switch, okay? So we don't have a whole lot of control with the starter. It's either on or off. We're usually going to see starters on lower horsepower motors. The second thing we're going to see are soft starters. Now, in my experience, soft starters are becoming a bit antiquated, but they are still an option for you guys if you do choose to do so. What a soft starter is a soft starter is slowly ramping our motor up to 100%. So think of a soft starter like one of those newer buildings where you walk into a room and the lights kick on. The lights are kind of dim at first, and they slowly get brighter. Essentially, that's exactly what a soft starter is. We don't want to kick that system all on full blast at once. We want that motor to slowly get to where it needs to be based on some sort of time or something like that. And then finally, we have our variable frequency drives. So our variable frequency drives are essentially able to modulate the frequency of the motor. So the VFDs are just speeding up and slowing down our motors based on what you're telling it to do. So drive is kind of a funny term, right? Think about driving a car. A drive is like a gas pedal, okay? So your gas pedal, you're just telling your motor to speed up or slow down based on certain conditions in your building. Okay, go ahead. So the basic VFD configuration is going to look like any other motor control setup that you guys are going to see, okay? So VFD configuration is going to be very similar to a starter. It's going to be very similar to a soft start as well. So one thing to point out, VFDs are not generating voltage, they're not generating current, okay? So all a VFD is doing is it's allowing current to pass through and then go on to your motor. So we've got our line power coming in. Let's say we've got 460 volts coming in. We've got that line power coming in. It's going into your VFD. then it's going and it's actually talking to your motor. It's telling your motor what to do, okay? Maybe your motor is speeding up, slowing down. There's going to be some sort of process output that's telling our VFD to speed up or slow down. Okay, so let's think of an example. Let's think of just the temperature in a room. Okay, it's going to get hot enough in a room. Excuse me. Let's say it gets up to 72 degrees in the room. We want our air conditioner to kick on in that room, but as it progressively gets warmer, we want that air conditioner to work harder and harder, right? So what's happening is that thermostat is telling our VFD exactly what the temperature is, and then that VFD is responding with the appropriate amount of airflow in order to cool that room down, okay? Go ahead and move to the next slide. So here is kind of exactly what's going on inside the VFD. Now this isn't critical. This is really just to kind of give you guys a little peace of mind as to what's actually happening inside your drive. So you've got your AC voltage coming through. Okay, so let's say you've got 460 volts AC coming through. That AC voltage is hitting your rectifier bridge or diodes. So each one of these 6 little triangles that you can see on the left side of your drive are the diodes. Now what's happening at the diodes is we're converting that AC voltage to DC voltage. Okay? The reason we convert AC voltage to DC voltage within a drive is so that we can better control the actual speed of the motor, okay, or the frequency that's being output by the drive, okay? So in that rectifier bridge, we convert AC voltage to DC voltage. DC voltage, that voltage is then stored in the capacitors, okay? Now this is where it gets kind of interesting because in the capacitors, we still have to give voltage to our motor, right? So the DC voltage is being stored in those capacitors. You see those little 6 round things on the right-hand side of the drive? Those are called IGBTs. And basically what those IGBTs are acting as is they're sort of acting as little timers. The IGBTs are looking at that DC voltage. They know what speed our motor wants to be run at. And those IGBTs are releasing voltage in pulses. Okay, so it's very steadily releasing voltage based on a certain time, and that timing is based on the frequency that you want your motor to be running at. So in this case, let's say we want our motor to be running at 30 hertz. We're going to run that motor pretty slowly. Those IGBTs are releasing that current in a 30 hertz fashion. This is called pulse width modulation. Pulse width modulation is a very common term. Many other drives utilize the pulse width modulation terminology or technology. So basically what we've got going on here is we've got our AC power coming in, it's being converted to DC, and then that DC is being pulsed out to our motor. The motor is an AC motor, right? So essentially what's happening with that pulse width modulation is we're tricking our motor into thinking that it's receiving AC voltage, okay? It's receiving DC, but that pulse width modulation is making the motor think that it's AC voltage, okay? If you guys have any questions about that, definitely raise your hand and we can address those later. So input, you've got your fixed voltage, fixed frequency. On the output side of things, variable voltage, variable frequency, all based on how fast we want to run that motor, okay? Next slide, please. So why do we care about using drives? I mean, why is this important for you guys, and why is this helping with your applications? Well, first and foremost, we're going to see a reduced energy consumption, and I'll show you guys a slide about kind of the affinity laws and what we can do if we turn down the speed of our motor. But we're going to save ourselves a little bit of energy with the drives. Then, of course, we're going to have improved process control and efficiency. So when we can control the speed of our motor, we gain a lot of benefits and we have a lot more flexibility. So when we have the exact output we need, we're able to be much more efficient. It can also help improve the actual quality of the equipment that you're working on, okay? So you're not having to go out and do a bunch of maintenance on a bunch of equipment. This VFD is actually helping your piece of equipment run better. With expanded automation and integration, we're just saying that you guys can use this on essentially any motor that you need to use it on, especially with the LinkSpring VFD. This is a multi-purpose drive, okay? So this drive, you go in and set your application, and you can essentially run it on whatever it is that you need to run it on, and it's going to be able to communicate with any sort of building management system and any sort of communications protocol. We have a lot more flexibility with drives. So let's say you have, for whatever reason, you have a 20 horsepower drive sitting on your shelf left over from another job. That 20 horsepower drive can be used on any motor 20 horsepower and below. So all you do is take that 20 horsepower drive and set it for, your 5 horsepower motor that you need to be running it on. So you've got a lot more flexibility with your drives. And then as the years have gone on, drives have just become much more reliable, much more affordable, and much more available to you guys. So in a lot of cases, a drive is going to be a much better option than a starter. Go ahead and go to the next slide. So this is kind of what I was talking about with the efficiency savings that you guys can expect to see. So when we're running our motor across the line, 60 hertz, we're running it all out 100%, we're letting that thing go, right? So running that at 100%, and that's fine if you need to be running your motor at 100%. But a lot of the time, we don't need to run that motor at 100%, and so by turning your VFD completely on and letting that thing run at 100%, we're not acting as efficiently as we could be acting. So in a VFD's case, let's say we turn the speed down by 20%, okay? We take from running at 100% and we turn it down and we run it at 80%. We're going to see a 50% reduction in energy, okay? Let's say we turn the VFD down by 50%. We're going to see an 80% reduction in energy, okay? So really important to kind of look at where your motor needs to be run at and see some energy savings there. Furthermore, you do have access to a VFD savings calculator, okay? So this is kind of an example that we have on our website, and basically what you'll do is you go in and you plug in all of your job site data. So you're plugging in your motor horsepower, when you're going to be running it, your voltage, what the application is, all the pertinent information. And from there, it's going to actually spit out the KW per year saved, the annual savings you can expect to see, and when you can expect to be paid back. So I don't know if you guys can see that arrow at the very bottom of the page, but that says months to payback, almost 5 months. So that drive is going to pay for itself in 5 months. All right, next slide. So let's talk about the P-Series VFD that you guys have access to. If you just want to go ahead and click the arrow, the next arrow. So the P-Series drive, it has a lot of the same features and functionality that any other manufacturer's drive is going to have, okay? What this drive has that's really special is what's called Fast App firmware, okay? So this Fast App firmware has HVAC-specific applications built right into it. So let's say you've got a cooling tower, right? You're going in, you're going to set up your drive, you're setting it up for a cooling tower. When you go and select the cooling tower application, what's going to happen there is it's going to go ahead and pre-program all default settings for a cooling tower. So what's happening is you're essentially just saving yourself a few steps by being able to exactly select the application that you're using for this drive. This drive is going to be able to communicate BACnet, LAN, Johnson Controls into. It'll communicate with any sort of DDC system that you need. We've got dual PID mode. It's going to meet all of the standards that you need it to meet. This is basically your robust, full-featured drive that's going to compete with any other drive and any other spec. You have that available to you up to 700 horsepower off the shelf. Next slide. So a couple different options we have as far as packages are concerned. The first one we're going to see is just your basic standalone drive. That standalone drive doesn't have a line reactor, it doesn't doesn't have a disconnect. That's just what we call a bare bones drive, bare bones NEMA 1 drive. Our second option is going to be our drive with a disconnect, okay? So a lot of times people will elect to put a disconnect upstream of their drive. You can get that package with LinkSpring as well. So you'll still get your bare bones drive, but then that drive will also come with a disconnect in that cabinet that will disconnect power to the drive should you need it to. That cabinet can also come with a 3% line reactor as well. And then finally, we've got our VFD with a bypass. Now, what a bypass is doing is a bypass allows you to bypass the drive should you need to. So let's say you're having some sort of issues with your drive, you need to replace it or something's going on. What the bypass is the bypass is an across-the-line starter that's still connected to your motor. So you can still run your motor even if your drive is offline, okay? So having that bypass is basically just a backup system. If something fails in the VFD, that bypass will automatically kick over and you won't have any downtime. The bypass will just pick up where the drive left off. Now, bear in mind, that bypass is just a starter, okay? So that bypass is going to run 100% on, 100% off, right? So you will be running your motor at 60 hertz, but in a lot of cases, it's better than not being able to run your motor at all. Right? Another option with that bypass is to include an AC line reactor. Next slide. So speaking of line reactors, let's talk a little bit about line reactors and kind of what you guys can expect. So the reason we include line reactors and reactors is because of harmonics. So basically drives generate harmonics, okay? Harmonics generate extra heat. They can cause equipment to malfunction. Harmonics in and of itself are its own 30-minute webinar, and so I'm not going to really delve into harmonics too much. But basically, drives generate harmonics, and so if we're going to use drives or any other nonlinear equipment, the engineering community says that we have to meet a standard called IEEE 519. IEEE 519 is basically saying that we're doing something to help mitigate those harmonics created by our drive, okay? Now what you can do with this LinkSpring drive in order to mitigate those harmonics is you can have a 3% or a 5% line reactor installed just before the drive, okay? That 3 or 5% line reactor is helping you meet the IEEE 519 and it's smoothing out the harmonics, okay? So to be on the safe side, when you guys are going in and selecting product, I almost always include a line reactor with my drive just because I know that engineers want me to meet that IEEE 519. And so I want to make sure my bases are covered, right? If you don't need it, you don't need it, but it's always a good idea to include it on the front end just to be safe. So we've got our line reactor, we've got our drive, and then we've got our output reactor, okay? Now an output reactor is protecting our motor on the output side of things. So the output reactor is cleaning up the output side of the drive. Now, typically in HVAC applications, we don't need an output reactor. Reason being is that the drive is usually going to be mounted pretty close to the motor, okay? So our rule of thumb is 100 feet. If your drive is going to be mounted over 100 feet from your motor, we're going to go ahead and include an output reactor, okay? Where we really see output reactors more would be in our pumping applications, so our groundwater and irrigation applications where a drive is mounted in a pump house and the motor is, 200 feet down in a well below the water. I'm sorry, below the ground. That's where we're really going to see output reactors and output filters more often. But again, 100 feet is a good rule of thumb. If your drive is going to be mounted more than 100 feet away from your motor, go ahead and throw an output reactor on there as well. One thing to also kind of keep in mind, and I can't remember if I even made a slide about this or not, but When we're talking about line reactors, you may have also heard the term DC link reactor or DC bus choke. So the DC link reactor and the DC bus choke are installed after those diodes in your drive. So they're installed about halfway through your drive. Okay? The problem with this is that you're leaving those diodes and that rectifier bridge, the whole front part of your drive is being left unprotected. So those are still subject to the harm that harmonics can do. That's why we at LinkSpring and at FCS elect to use a 3 or a 5% line reactor on the very front end of the drive so that we ensure that the entire drive is protected, not just the back half. Okay? Go ahead and go to the next slide. Awesome. So that's it. Looks like I did it in just under 20 minutes to leave you guys plenty of questions for Q&A. Tanya, if you want to go ahead and get the Q&A started, I'm happy to help.
Great. Thank you so much, Margaret. We appreciate your presentation today. It looks like one of our first questions it is in regards to what different enclosure ratings can you get?
Yeah, okay, so NEMA 1 is going to be kind of what we typically see. So NEMA 1 is going to be installed in your mechanical room. NEMA 1 is indoors. It's not going to get a bunch of corrosion and dust. NEMA 1 is just basically inside. Then we can also do NEMA 3R. Okay, so we can do NEMA 1, NEMA 3R, and then we can bump up from there. We can do NEMA 4, NEMA 12. We can go 4X. We can go 4X fiberglass, 4X stainless steel. Now, one thing to keep in mind when we're going fiberglass, 4X fiberglass or 4X stainless steel, these drives are generating heat, right? So you put those things in an enclosure, that enclosure is going to get hot. So we have to do something to help with that heat inside of that enclosure. So when we start talking about 4X, we're also having to talk about putting an air conditioner inside of that enclosure. So just something to bear in mind. If we do need to go 4X, you know, a coastal environment, for example, is going to require 4X because it's corrosion resistant, and you can put it outside where it's taking the seawater. Just something to bear in mind is to make sure that those enclosures are being cooled down with some sort of air conditioning system in there. Any other questions?
Okay. Yes, looks like, what about temperature restrictions?
So that's a good question. So the drives are rated up to 104 degrees. 104 degrees is as hot as we can get inside that enclosure. Let's say we're putting these drives on a rooftop in Houston, Texas. It's going to get hot on that rooftop in Houston, Texas. So there's a really simple way around this. What we'll do in that case is we'll do what's called derating the drive. All derating means is that you bump the drive up to the next size, giving yourself a little bit more flexibility for heat, okay? So when we derate the drive, we're giving ourselves up to 122 degrees Fahrenheit, which should be plenty of room for us. Another note about derating is we're going to be putting these in elevation. So anywhere 3,300 feet or higher, we'll also want to derate the drive. So just bump up to the next size. If we're using a 7.5 horsepower drive, but we're putting it on the top of a mountain, we're probably going to want to bump up to a 10 or maybe even a 15 horsepower drive.
All right, thank you. Looks like, how about support and startup?
So we actually have a startup video that I can share with you guys. The startup video basically just goes through your basic startup of one of these drives. We can also conduct webinars with you guys going through startup, making you guys trained, certified startup people. A lot of times on a job site, the spec will require that the person out there is a certified startup or certified technician for one of these drives. We can make that happen for you guys. So if you want to learn how to start these things up and become certified, what we'll do is we'll go through an hour webinar with you all. We'll teach you all the ins and outs of the drives, how to start them up, how to troubleshoot them, common issues that we've seen in the field, and how to wipe those issues out. And then after that, you will be a certified LinkSpring/FCS startup technician, and you'll be able to do startup on essentially any job site that requires that sort of certification. As far as support goes, we're a small company just like LinkSpring, and we understand that a lot of the time you guys have issues and there's a gun to your head and you've got somebody screaming at you to resolve the issues. Because we're this small company and we're this kind of used to be no-name company, we know that we have to be on the forefront of supporting our customers and getting the issues resolved quickly and efficiently. So if you do have any issues in the field, we really invite you to call our tech support team. We're very proud of our tech support team. We have a meeting every day where we talk about how many calls they took and how long a customer was on hold and did the customer need to be called back. And like I said, we're very proud of our tech support team, and we really monitor, what it is that they do, and it's very important to us that we fully support our customers with our products in the field.
Great. Looks like we have another question for you. Please explain cautions concerning power disconnect switches downstream of the VFD at the motor.
So by that question, are you meaning like the late break, early make type situation?
I'm not positive. One of the questions just came in.
What we'll typically do is we'll install a disconnect ahead of the drive. What we're seeing is, as far as protecting our motor from like putting disconnects after the drive, is a situation called late break, early make. And that's not something that we will typically do. That's typically going to be provided by others. I hope I'm answering the question sufficiently. We're not typically going to install a disconnect after the drive.
All right. Well, thank you, Margaret. It looks like that's all we have for questions, right? Oh, here comes another one that just came in. Let's see, cooling tower application. Disconnected switch is outside. So I guess that's going to follow up to the previous.
Cooling tower application, disconnect switch is outside. So is the disconnect switch, I don't know, I feel like I need to just talk to this guy. Because it sounds like maybe the disconnect, yeah, maybe you could hook me up with this guy and we can kind of talk about exactly what his application is. We can kind of get that figured out.
We will. We'll go ahead and forward you that specific question to answer in more detail. And we are grateful for everyone who was able to attend an hour early for this month's 30 Minutes with LinkSpring. And please join us again next month for another edition of 30 Minutes with LinkSpring. For a regularly scheduled day and time, the third Wednesday every month at noon, Central Standard Time. Again, we thank Margaret Shaw with Franklin Controls, and we are so excited that she was able to join us and present to us today. Thank you, and everyone have a great day.
Thank you, everybody.